Hello students, this lesson is part 2 of a 3-part series on limits. Give the domain of each function below, then graph each function using technology, comment on any differences. Now the first function is f of x equals 2x. You can double any number, so the inputs x can be any real number. So the domain is x can be any real number. This symbol right here means is an element of, and we have interval notation from negative infinity up to positive infinity. Or you can say that x must be somewhere in between negative infinity and positive infinity. This function has the form mx plus b. It is a linear function. M is 2 and b is 0. So we know that the line will go through the point 0, 0, and then the slope is 2, so go right 1, up 1, which takes us to the point 1, 2. And then draw a line connecting these points. Now let's look at the next function, g of x. At first this looks a lot more complicated. Let's do its domain. Notice there's a denominator. You cannot divide by 0, so x cannot be 1. Using a number line to represent the domain, at 1 we would have a hollow point because x cannot be 1, and then we get to shade either side of it. In interval notation, we would say x is an element of the interval from negative infinity to 1, union from 1 to infinity. Now this first interval corresponds to this left shaded part of the number line, and the second interval corresponds to the right shaded part of the number line. Or we can simply say that x has to be less than 1 or x has to be greater than 1. In Desmos, I have the two functions graphed, f of x equals 2x in red and g of x in blue. Now if you do a trace by clicking on the blue graph and trying to get to this location, you'll notice a hollow point when x is 1. So we have 1, undefined. That's because x cannot be 1 in this function. Otherwise, the two functions look identical. Now the graph of g of x looks continuous when you graph it in Desmos. It does not automatically show you that there's a missing point when x is 1. If you want this missing point to be shown permanently, then you have to type in the point 1, 2, then make it blue, and then make it hollow. And this will leave a hollow point in the correct position permanently. Back in our notes, let's graph this hollow point at 1, 2, and then graph the rest of the line. Notice that the two functions are identical, except that g of x has a domain restriction at 1, hence a missing point at 1, 2. Now we can consider the limit as x approaches 1 from both sides of g of x, and we will get a value of 2, which is the y-coordinate of that missing point. Similarly, we can do the limit as x approaches 1 of f of x, which is a continuous version of g of x. And we're also going to get a limit of 2. Now why are these two functions so similar? Notice that we can take g of x and we can simplify it. We begin by factoring the numerator by factoring a 2x from both terms. So the numerator becomes 2x times parentheses x minus 1. And now we can cancel with the x minus 1 in the denominator, leaving just 2x. So if I want to find a limit as x approaches 1 of g of x, I begin with g of x, this function, and then simplify it to this function 2x, which is continuous, this graph here, and then plug 1 into the continuous version to get 2, and that will be my limit even for g. Now consider doing this backwards. Let's say I want to have a graph of y equals 2x, but I want to remove the point 1, 2. I simply have to multiply 2x by x minus 1, and then divide also by x minus 1. That will have the effect of removing the point from the graph y equals 2x corresponding to x equals 1. Continuing on, find a function that is identical to the function h of x equals square root of x, but for which the point 4, 2 is removed. Well, let's call this h sub 1 of x equals square root of x because I'm about to create a new function h sub 2 of x which has the point removed. We begin by writing the rule square root of x, and I focus on the x-coordinate 4 of this point 4, 2. I want a domain restriction that x can't be 4. So I multiply square root of x by x minus 4 over another x minus 4, which I can then write in this way, and now distribute the square root of x. So we get x square root of x minus 4 square root of x all over x minus 4. Now I can write this another way. Keep in mind that the square root of x means x to the 1/2. Well, that's x to the 1 times x to the 1/2, and I would add the powers. So I can also write this, therefore, as x to the 3/2 minus 4 square root of x all over x minus 4. So in Desmos, here are my two functions. h1 is the square root of x in red, and h2 is the function I created in blue. Now they look identical except for the fact that h2 has a domain restriction at x equals 4, hence there's a missing point in the graph. You can find the output coordinate of that missing point by looking at the continuous version, which is the red graph, and seeing that the output is 2. Now find a function that is identical to the function k of x equals e to the x, but has removable discontinuities at x equals -2 and 0. So again, I will call this k sub 1 of x equals e to the x, and we're going to create a k sub 2 of x. To make this new function, we begin with e to the x, and we want to remove a point corresponding to when x is -2. So I would multiply e to the x by x minus -2 over another x minus -2. And that's just x plus 2 over x plus 2. Now I want a discontinuity when x is 0. So I'm going to multiply this yet again by x minus 0 over x minus 0, which is just x over x. So here's my final result without doing any distributing. Now let's go to Desmos. k1 in red is a graph of e to the x, and k2, the function I created, is identical in shape. However, k2 is undefined when x is -2, and undefined when x is 0. Okay, let's go to the next page. Given the rule of a function f, there are several methods for determining whether a limit exists, and if so, its value. If the function is continuous at x equals a, then the limit as x approaches a of that function is f of a. Now what this is saying is that, let's say you have some function that's continuous at x equals a. So there'd be an implied point here, whose coordinates would be a, comma, f of a. Now as x gets closer to a from the left, the outputs of the function get closer to this f of a. And as you approach a from the right, the same thing happens. So if you know that a function is continuous, finding a limit is as easy as plugging in that value a into the function and getting the y-coordinate. Now, if the function is not continuous at x equals a, then consider the following. You can predict the limit by making a table of values using technology, if available, as x approaches a. Number 2 is you can predict the limit by producing a reliable graph using technology, if available. And 3, you can algebraically simplify the function to create a continuous variant function g of x, and then evaluate g of a. If they exist, find the limits below using more than one method for each. In this first case, we have a function 3x plus square root of x. 3x is a continuous function no matter what x is. The graph of it is just a line. Square root of x is continuous if x is bigger than or equal to 0. So overall, this function will be continuous for all x is bigger than or equal to 0. Well, 4 falls within this window. So in other words, we can find this limit by simply evaluating the function at x equals 4. Plug 4 in. We get 3 times 4 plus the square root of 4. That gives us 12 plus 2, which gives us a limit of 14. As a second method, we'll use technology. Here's a graph of the function. I'm going to change the y scale so we can see it a little bit better. And then notice that it's continuous. In fact, as x approaches 4, we can see that there's a solid dot at the location 4, 14. So 14 is the limit of this function as x approaches 4 from both sides. You can also make a vertical line at x equals 4, and then click on either graph to show the point of intersection. This way you don't have to click and drag along the function, and you can see the points of intersection permanently. Now let's look at the middle limit. This function has a denominator, and denominators cannot be 0, which means that x cannot be 3. So this function has a discontinuity at x equals 3, which is precisely the value of x that we want the limit to approach. Furthermore, notice that if you try to plug in 3, not only will the denominator get closer to 0, but so will the numerator. 3 squared is 9, minus 2 times 3, which is minus 6, and then minus 3 will give you 0 in the numerator as well. So this fraction approaches 0 over 0. In mathematics, this is called an indeterminate. It is not equal to 1. You can never divide by 0, and 0 over 0 is an inconclusive state. What this means is that we need to do further analysis. Now I'm going to do method number 3 of algebraically manipulating this. In this case, we can factor the numerator. The x squared factors to x times x. And now we need two numbers that multiply to -3 but would add to -2. That will be -3 and +1. And our denominator is still x minus 3. And we're still doing a limit as x approaches 3. Notice that these two factors can now cancel. And we can simplify this function to x plus 1. This new function is continuous at 3, so we can find this limit by plugging 3 in. And 3 plus 1 gives us 4. As our second method, I will use technology. Here's a graph of the function, and sure enough, if I do a trace, you will see that at 3 we have undefined for the output. And the location of that hollow point is 3, 4, confirming the limit is 4. In this last example, as x approaches 0, 2x approaches 0, e to the 0 is 1, times 3 is 3, and then minus 3 will give us 0. And of course, this x approaches 0. So this fraction also approaches a 0 over 0, an indeterminate state. However, we cannot use the third method here. There is no way to algebraically manipulate this in a productive way. So that leaves us methods 1 or 2. And we'll use technology for both of them. Here's a graph of the function. And as I get closer to x being 0, notice that we do have a point 0, undefined, confirming that we have a removable discontinuity and 0 is not in the domain. It appears that this location is at 0, 6. Let's go ahead and create a table of points using technology to confirm this. In Desmos, you can convert a function to a table. In order to do so, you need to change y to f of x or some other function notation. And once you've done that, you can click the gear symbol and then click the table next to the function. This defaults to several input values for x and will automatically compute the output values. Let's change these input values to numbers that are getting closer to 0. So I'm going to go ahead and delete them all. And let's pick numbers close to 0 but above 0, such as 0.1. Now let's get closer to 0. 0.01. Now 0.001. Now 0.0001. And notice that the outputs are, in fact, getting closer to 6. Let's get close to 0, but from the left. So -0.1, -0.01, -0.001, and -0.0001. And you can see that the outputs are still getting closer to 6. So this table of points does seem to confirm that the limit is, in fact, 6. So back to our notes. We'll summarize our answer by making the graph. Our graph looks something like this, but had a missing point or a removable discontinuity on the y-axis, and whose coordinates were 0, 6. Thus our final statement would be that the limit as x goes to 0 of this function is in fact 6. Let's go to the next page. If they exist, find the limits below using more than one method for each. Now you'll notice that I've switched some of my input variables to different letters. In this first case, my input variable is y. So when we make a graph, the horizontal axis will be y, not the vertical. The vertical axis would be some other letter. Now notice that if you did plug -2 in for these two y's, you would get a 0 over 0. So more analysis is required. We're going to use a table of points, and this time we will do it by hand. So our input will be a y coordinate, and our output some other coordinate. And let's pick some numbers that are left of -2, such as -3. You plug -3 in here, add 2 becomes -1, but then you do the absolute value of -1, which is +1. Now plug -3 for this y, add 2, we get -1. No absolute value this time. And 1 over -1 is just -1. Now let's get closer to -2. So maybe -2.1. Plug -2.1 in for y, add 2 becomes -0.1, and then do the absolute value. You get +0.1 in the numerator. In the denominator, you will get -0.1. And when you divide these, you get -1 again. In fact, you're going to notice that if you pick any y coordinate or input coordinate left of -2, even if very close to -2, that you're going to wind up getting an output of -1. Now let's explore to the right of -2. Plug -1 in for y, add 2 is 1, take the absolute value, stays 1. -1 for y, add 2, is 1. So we get 1 over 1 in this case, which is just 1. Now let's get closer to -2, but from the right. So let's try -1.9. When you plug in this value, you're going to get positive 0.1 in the numerator and positive 0.1 in the denominator and get positive 1. In fact, you could explore some more, and you will see that if you pick any y-coordinate that is more than -2, that the output will be positive 1. This suggests that we have a piecewise function at play. The output will be positive 1 if the input value y is more than -2, and the output will be -1 if the input y is less than -2. And the output will be does not exist if you try to plug in -2 itself. So graphically, -2 is an important transition location for our y-coordinates, for our inputs. If you're to the right of -2, the outputs are 1, with a hollow point on that orange line. If you go left of -2, then the output will be -1. This tells us that if I were to do a limit as y approaches -2 from the left of this function, I'll just say f of y, as we approach -2 from the left, the outputs are -1 and remain -1 and get closer to -1. So this limit is -1. But if I do a limit as y approaches -2 from the right of this function f of y, coming from the right, our outputs are 1, stay 1, and get closer to 1. So the limit is positive 1. These limits are not the same. So the two-sided limit as y approaches -2 of this function does not exist. In fact, we have a jump discontinuity at y equals -2. As a second method, we'll use technology. Now, in order to graph this, I do have to change the input variable back to x and the output variable back to y. So I type in y equals absolute value x plus 2 over x plus 2. This confirms what we did by hand. At -2, we have a jump discontinuity, and the function is undefined at both endpoints. Okay, let's do this middle case. This time it's h, that is the input variable. The output variable can be whatever letter. As h approaches 0, 2 times h approaches 0, and sine of 0 is 0. And this h here also approaches 0. So we do have another situation of 0 over 0, an indeterminate. We cannot algebraically manipulate this, so we will use technology. Once again, for technology purposes, we'll change the h input variable back to x and use y as the output variable. So here's our function. As we get closer to 0, we do see that we have a removable discontinuity. It appears that that location is at 0, 2. We're going to confirm this by making a table of points. Let's change this y to function notation such as f of x. Then click the gear and make a table. And let's delete these inputs and input numbers that are getting closer and closer to 0, such as from the right, let's begin with 0.1, and then 0.01, and then 0.001, and then 0.0001. And you can see we're getting closer and closer to 2. In fact, it's rounding to 2 at this point. Now let's pick some x's that are on the left of 0, such as -0.1. Now, closer to 0, -0.01, -0.001, and -0.0001. And you can see that, again, the outputs are getting closer to 2. In fact, they round to 2 at this point. So this confirms that the limit is 2. So copying our image over, we had a removable discontinuity at x equals 0, and the height of the missing point is at 2, and the rest of our graph looks something like this. The details don't matter. So in summary, the limit as h goes to 0 of sine 2h over h is in fact 2. Let's look at our third example here. X is once again our input variable. This is approaching sine of 1 over 0 as x approaches 0, but 1 over 0 does not exist. So we're going to use technology to help us determine what's going on here as x gets closer to 0. Here's the graph of this function. There appears to be some chaos near x equals 0. So we're going to zoom in here and then stretch the x-axis out so we can get a better sense. And even after I do this, I still see a lot of chaos going on near 0. So let's change our strategy to using a table of points. So change y to f of x and create a table. Now let's pick some x's close to 0, such as 0.1, now 0.01, 0.001, 0.0001, and I do not see any particular output that the function is approaching as we get closer to 0. This suggests an erratic behavior. I've created an animation here so that we can see that as we get closer to 0 with the x-coordinate and from the right, that the function just becomes more and more erratic, bouncing back and forth between 1 and -1, never stabilizing. Thus, the limit as x approaches 0 from the right does not exist. So in summary, we had some sort of function that got more and more erratic as we got closer and closer to 0 from both sides. As x approached 0 from the right, we did not have a limit, so we say DNE. As x approached 0 from the left, we had a similar situation. So certainly, as x approaches 0 from both sides, our answer is does not exist. All right, moving on to the next page. If they exist, find the rational function limits below using algebraic techniques. Now, a rational function, quick review. This is a fraction of polynomials. And a polynomial is a sum of one or more terms, and each term has the form ax to the n, where a is called the coefficient and can be any real number, but the exponent n must be a whole number. Whole numbers are 0, 1, 2, 3, 4, etc., the counting numbers. Now again, we're using different letters as the input variables. In this first case, we have two terms. This 4 is a polynomial term because you can think of it as 4, which is a real number, times w to the 0, because there is no w. The second term is also a polynomial term. -1 is the coefficient, and w squared. 2 is a whole number. In the denominator, this is a polynomial term, coefficient 1, and 2 is a whole number. This is a polynomial, -1 coefficient, and a 1 power on w, and 1 is a whole number. And this last term is a -2 coefficient, and you can think of this as having w to the 0, but 0 is a whole number. So we have a polynomial divided by a polynomial. This is a rational function. Now we're doing a limit as w approaches 2. If you simply try to plug 2 in, you will notice that you get a 0 over 0. This always suggests, in the case of rational functions, that you can factor and simplify. Now in the numerator, we see that we have a 4 minus w squared. That's like a 2 squared minus w squared. This is known as a difference of squares, and a squared minus b squared always factors into a minus b times a plus b. So I can factor that numerator to 2 minus w times 2 plus w. The denominator is a trinomial, meaning a 3-term polynomial. Try to factor it into 2 binomials, or 2-term polynomials. The w squared factors to w and w, and we need two numbers that multiply to -2 but add to -1. Those numbers would be -2 and +1. You should FOIL this to make sure that your factoring is correct. And we're still doing a limit as w approaches 2. Now this factor and this factor are pretty close to each other, but they're in reverse order. You can factor a negative out of one of these differences. Let's factor a negative out of the numerator. That would change that first term to w minus 2, and then we have a 2 plus w. And the denominator I'll leave the same. And now we can see we get cancellation of the w minus 2's, leaving us with this function. This function is now continuous at 2. So we can simply plug 2 in, and we get -4 in the numerator and +3 in the denominator. So this is our limit. Confirming with technology, and again switching the input variable back to x, we can see the graph of our function, and we see that we have a removable discontinuity at x equals 2. If we want to know the y-coordinate of this missing point, that's what the limit tells us, and we know that that limit is -4/3. Let's type in the point 2, -4/3, make it red and make it hollow so that that missing point is permanently visible. All right, the middle case. If you try to plug 2 in now, you will get another 0 over 0, suggesting we can factor both. The difference of squares in the numerator becomes x minus 2 times x plus 2, and we have a trinomial that factors into x minus 2 times another x minus 2. We get cancellation of this pair of x minus 2's. So we now have to do a limit as x approaches 2 of this new function. But notice this new function is still discontinuous at 2. In fact, it approaches 4 over 0. 4 over 0 is not an indeterminate. In the case of a rational function, this means that we're going to have a vertical asymptote at x equals 2. With rational functions, whenever you get a non-zero over 0, that'll be the indication that you have a vertical asymptote, which means that the limit as x approaches 2 of this function does not exist. Using technology to confirm, here's our function. Let's go ahead and put in that vertical asymptote. Let's type in x equals 2, and then make it blue and dashed. And we can see that as x approaches 2 from the left, that the limit will be -infinity, and as x approaches 2 from the right, the limit will be +infinity. So overall, the two-sided limit does not exist. Okay, now let's look at the third rational function. This time the input variables are z. This denominator suggests that z, and I cross my z's, cannot be 4. But notice that's not the z that we're approaching. Rational functions are always continuous for input values that are in their domain, and -4 is in the domain. So we can get the value of this limit by simply plugging -4 in. So we get -4 squared, which is 16, and then -16, all over 4 minus -4, which is 8. So this gives us 0 over 8. This is allowed, and 0 divided by 8 is simply 0. Here's a graph of our function using x as the input variable, and we can see that as x gets closer to -4 that the outputs get closer to 0. In fact, the function is continuous here, going through the point -4, 0. This function does have a vertical asymptote, but it's over at x equals +4, and we can zoom out to see that a little bit better. Okay, moving on to the next page. If they exist, find the limits below using algebraic techniques. Confirm by graphing with technology. In this first case, b is the input variable, and this is no longer a rational function because this term right here can be rewritten as b to the -1, and -1 is not a whole number. So technically we're not looking at what's called a rational function. This is, however, a complex fraction because we have two subfractions within the context of a larger fraction. Also observe that as b approaches 3, the numerator approaches a third minus a third, which is 0, and the denominator also approaches 0. So once again, this is a situation that's called an indeterminate, and it suggests more analysis is required. A great way to simplify a complex fraction is to identify the LCD of all the subfractions. There's two subfractions. Their denominators are different, 3 and b. Their lowest common denominator would be their product. If you multiply the overall fraction by this LCD over itself, and then in particular distribute across the numerator, observe what happens. 3b times 1 over b simply becomes 3. 3b times a third becomes b. The denominator I will leave factored. So I have b minus 3 times 3b. Now these two terms are opposites of each other. If I factor a negative out of one of them, then I will be able to cancel. Let's factor a negative out of the numerator. This results in the subtraction being reversed. The denominator is the same. And now we can cancel these two equal factors. So we get a -1 numerator over a 3b. This simplified function is now continuous at b equals 3, so we can simply substitute 3 in for b at this moment, and we get -1/9. Here is a graph of the function, and sure enough, at 3 we see a removable discontinuity, and we now know that that missing point would have coordinates 3, -1/9. Okay, looking at the second example, h is our input variable. As h approaches 0, the numerator approaches square root of 9, which is 3, minus 3 is 0, and the denominator h also approaches 0. So once again, we have an indeterminate form. Let's do some algebraic manipulation. Now the structure of the numerator is a difference, a minus b. What we're going to do is we're going to multiply the numerator and denominator by the conjugate of this term. Now the conjugate of a minus b is a plus b. And a minus b and a plus b are called conjugates of each other. So let me rewrite the problem. I'm going to multiply the numerator and denominator by the conjugate of the numerator. So 9 plus h and then plus a 3. Same thing in the denominator. Now this will be useful because when you multiply conjugates, a minus b times a plus b, and you FOIL, a times a is a squared, plus ab, minus ab, and then minus b squared. The two middle terms will cancel each other, and you'll simply get a squared minus b squared. So over here, let's FOIL. A radical times itself winds up being the square of that radical, canceling the radical. So we get simply 9 plus h. Then we're going to have plus 3 times radical 9 plus h, and then minus the same thing, and then minus 9, all over. And then for the denominator, leave the h factored out, and then just write the conjugate in some parentheses next to it. Sure enough, several things in this numerator are going to cancel. The two middle terms are gone. Also, the 9s will cancel, leaving us simply with h all over h times this conjugate. And now we can cancel the h over h, giving us 1 over this conjugate. This simplified function now is continuous at h equals 0, so I can simply substitute h equals 0 in and calculate. And we wind up getting 1 over square root of 9 is 3, and then add another 3, so a final result of 1/6. Here is a graph of the function. I had to use x as the input variable instead of h. Sure enough, at 0 we have a removable discontinuity, and we just discovered that that missing point would have coordinates 0, 1/6. Okay, now let's go to the next page. Graph the piecewise function below and give the x value of each discontinuity. Then classify each discontinuity by finding each one-sided limit at that x value. This is a piecewise function. I'm going to color code this. I'm going to focus on this first piece. That -1 power simply means you do the reciprocal. So we're looking at graphing this function, and we'll do this by hand. Well, this is a transformation of simply 1 over x. 1 over x is one of our basic functions we should be comfortable with. It looks something like this. It does pass through 1, 1 and negative 1, negative 1. It has the x and y axes as asymptotes. Now when I change the x to x plus 2 instead, this corresponds to a shift left 2 units. So imagine this function now going left 1, 2 units. The new vertical asymptote will be at x equals negative 2. Now we're going to crop this function. We're going to keep the portion of the function dictated by this interval. X is an element from negative infinity up to negative 2, excluding negative 2. This portion of the curve corresponds to inputs greater than negative 2, and so it should be eliminated, and we only keep the left portion. Okay, now let's graph this portion of our piecewise function. 3 minus 2x, this is the form mx plus b, where m is negative 2 and b is 3. This is a linear function, passes through 0, 3, and has a slope of negative 2. So I'd go right 1, down 2. A second point should be 1, 1. I could continue, but we have a line. Here's the line in its entirety, but now we only want to keep the portion of the line between negative 2 inclusive and 1 exclusive. Plug negative 2 into this linear function, you get 3 minus 2 times negative 2, or 3 plus 4, you get 7. So our line does go through this point, negative 2, 7. It will make a solid point there because of the inclusion of negative 2 due to this bracket. This 1, though, has a parenthesis. So we're going to find the point when x is 1, but then exclude that point. So I'll put a hollow point at 1, 1. And then we only keep the portion of the line in between these x coordinates. Now let's focus on the third portion, x squared. X squared is just a basic function parabola. Has a vertex at the origin, also goes through 1, 1, goes through 2, 4, etc. And we want to keep only the portion of this parabola between 1 exclusive, 2 inclusive. So we'll have a solid point at 2, 4 and another hollow point at 1, 1 and keep only this portion of the parabola. And then finally, we'll graph negative 3. That's a constant output. So we'd have a horizontal line at height negative 3, and we're only going to keep the portion from 2 exclusive up to infinity. So let's put a hollow point at 2, negative 3, and then keep only to the right. And this is our piecewise function. Let's identify where the discontinuities are. If trying to draw this without lifting your pencil, you would have to lift your pencil for this x-coordinate, this x-coordinate, and this x-coordinate. Otherwise, the function is continuous. We have discontinuities at negative 2, 1, and positive 2. Let's do the left and right limits and the two-sided limit at each of these locations. As x approaches negative 2 from the left of this function, we can see that the outputs of the orange curve are approaching negative infinity. So that is our limit. But from the right, we look at the blue curve, and as we approach negative 2 from the right, the outputs are approaching 7. So the limit as x approaches negative 2 from the right is 7. Now these limits are different, so the best thing we can say about the two-sided limit is does not exist. And because one of the one-sided limits is infinite, we have an infinite discontinuity at x equals negative 2. Now let's focus at x equals 1. From the left, we look at the blue curve, and as we get closer to x equals 1, the outputs get closer to a height of 1. And if we approach x equals 1 from the right, we look at the green curve, but the outputs here are also approaching a height of 1. So both one-sided limits, the result is 1, so the two-sided limit is 1. However, there is no point there, so this is a removable discontinuity at x equals 1. Now focusing on the discontinuity at x equals 2. From the left side, look at the green curve, but get closer and closer to an input of 2, and the outputs get closer and closer to that green solid point whose height is 4. So as we approach 2 from the left of this function, we get 4 as the limit. Now we look to the right side of x equals 2, which has us looking at the red curve, and as we approach 2 from the right, the outputs are equal to and remain equal to and get closer to negative 3 as an output. So our limit as x approaches 2 from the right is negative 3. These numbers aren't the same, so the two-sided limit we say does not exist. And because the one-sided limits exist and are both finite, this is called a jump discontinuity at x equals 2. To graph a piecewise function using Desmos, type in the first piece, x plus 2 raised to the minus 1. And then to crop it, you put curly brackets next to the function rule, and you use an inequality, not an interval, and say x is less than negative 2. Make it orange. Then also I'll graph the vertical line, x equals negative 2, and make it dashed in orange. Now we'll graph the middle piece, 3 minus 2x, make it blue. And then curly brackets, say x is greater than or equal to negative 2, but strictly less than 1. Now if we want to make these points be solid and hollow permanently, we'll have to type them in separately, and then format them so that they are solid or hollow as appropriate. Now we'll graph the third piece and make it green, x squared. Next to that, curly brackets, and then say x is greater than 1, but still less than or equal to 2. I already have a hollow point at 1, 1, so I'll just make a solid point at 2, 4 and make it green. And then the final piece is just negative 3. I may have to say y equals negative 3 to see it. Make it red, curly brackets next to that, and say x is more than 2. And then let's put a hollow red point at 2, negative 3. And here we have Desmos graphing our piecewise function. All right, this concludes our second part of a 3-part series on limits.